Okay, guys, welcome. Today we're going to talk about natural exponential and natural logarithmic functions. So, of course, these things come up naturally, hence the name in mathematics. So it's worth our while to talk about them, right? Now, the first thing we're going to talk about is what's called the natural base, which is known as the number e. Right, so you are hearing me correctly. So we represent it with an e, but it does represent a number. Right. So now all that you need to know about E in this video is that it's roughly 2.7183, right? Now you could, if you're interested, you could, find on the internet how you could obtain this number E, but it involves a little bit of sort of a calculus kind of argument. So we're not going to cover it here, but all that we need to know for now is that E is this number that's roughly equal to 2.7183. All right. And of course, if you wanted to talk about a natural exponential function, this is just an exponential function where this number E is your base of your exponential function. All right. Now, of course, whenever you talk about a natural base, you can also talk about its related natural logarithm. So now if you see a natural logarithm, that is just indicated by ln of x. And that is just saying that we have a logarithm where the base is that funny number e, right? So if you see ln of x, that just means a log with base e. Okay, and of course we could then talk about the natural logarithmic function, where now we're just saying that this is a relationship between x and y. And again, just keep in mind that natural log of x is really a log with base e of x. All right, and then of course finally, if you have that y is equal to ln of x, if you were to convert this to exponential form, this just means that e to the y is equal to x, right? Because your base of your natural log is e. All right, so that's what we mean by that. Okay, now we're going to derive a couple properties using the exponential form here, right? So what's the natural log of 1? Well, we don't know what it is just yet, so we're going to call it x. And now we're going to convert this to exponential form. And again, since ln of 1 is really like a log base e of 1, what does this mean? That really means that e to the x is equal to 1. Well, how do you raise any number to a power and get 1 to come out? You just need x to be 0. Right? And if you want, you could say that 1 is also e to the 0. All right, so that's the first one. Now, we said in part A that the natural log of 1 was 0. So 2 times the natural log of 1 is just 2 times 0. So this should also be 0. Right? But if you don't want to think of it that way, just think of this as, again, being equal to x. And then before we do anything, we need to divide the 2 over. And of course, this says that e to the x over 2 is equal to 1, but this doesn't change the fact that x would still need to be 0. All right, so you can also see it that way. All right, well, what about if we want to find the natural log of e? Well, if we call this equal to x, this really says that we have a log base e of e equal to x. So now if we write this in exponential form, this says that e to the x is equal to e. And of course, if you don't see an exponent, we have that a 1 is there. So this allows us to say that x would have to equal 1. Right? Now in part D, you could use either one of the same arguments that we use in part B. We could say this is 2 times the ln of e, which we just found to be 1. So we should get 2 for this. Or you could say that 2 ln of e is equal to x. So then once you divide both sides by 2, you get that ln of e is equal to x over 2. And then if we write this in exponential form, we get that e to the x over 2 is equal to e. And again, if you don't see the exponent, it's understood to be 1. So then we can say that these two things must be equal. And once you multiply by 2, you get that x is equal to 2. All right, so that's another example where you could show it one of those two ways there. Okay, now how do you find sort of these natural logs and this e expression on your calculator? Usually they're pretty close by. So on an older scientific calculator, again, this is one of those things where you would either need to type your argument or your exponent of your logarithm or your exponential, and then actually hit ln or e after that, and then that would return the number to you. However, on most calculators, you can just, again, type it as you see it, and you could, for example, do ln of 31 and close it, and then once you hit enter, it'll give you the answer, right? So it'll be roughly 3.43398, and so on, right? And usually the ln and the e are pretty close by, and on many calculators, usually there's an ln button, and then if you hit second and that ln button, that gives you the e, right? And that's usually how it works on most calculators. Okay, but anyway, let's figure out some approximations with e and natural log here. So on this first one, again, this is just sort of more practice of evaluating these in the calculator. So on this first one, I want to find e to the 3.098. So we go to our calculator. Now on my model, the ln button is 2 keys below the second button. And I would also need to press second and ln to get to my e. So I have e to the 3.098. And if I type that in, I'm going to get 22.1536 roughly. And again, this is rounded to 4 decimal places. So I get roughly 22.1536. All right, in part B, so same thing. I want to find e to this power, so I need a negative 0.247. And if I type that in, I'm going to get roughly 0.7811. And that is a couple examples of finding some e values in your calculator. Now, sort of in the same idea here, we want to solve these simple natural log equations. And what this is really going to boil down to is once we convert this to exponential form, we're going to get e to the 5.903 is equal to x. So I'm really just finding some more powers of e in my calculator. So if I want e to the 5.903, okay, we type that in. We're going to get that x is roughly 366.1342. All right, so that's that one. In part B, again, same idea. We want to convert this, so I want to say this is e to the negative 1.362, and that will give me my x value. So if we type this in, negative 1.362, we're going to get that this is roughly 0.2561. All right, so that's solving a couple of these simple natural logarithmic equations. Okay, now the next thing that we're going to talk about is our change of base formula, right? So we have already mentioned this in a previous video, but here we sort of formally talk about it again. Now, the way that the change of base formula is presented is not necessarily useful to us right away. But of course, one thing that we can do with the change of base formula that is useful is convert the both logarithms to common logs, or you could actually even use natural logs as well. You could say it's natural log of x over natural log of a. Right, so we could also do that as well. All right. So for example, if we wanted to find log base 5 of 79, well, then by the change of base formula, we could say this is a common log of 79 over a common log of 5. So if we evaluate this, so again, we'll let the calculator do the work. So this is log 79 over log of 5. And this will give us roughly 2.7149 if I round to 4 decimal places. Right. So again, you can use the change of base formula. The advantage of that is bases that are not 10 or E, we would need to use, you can't find a button in the calculator that would do this for you. So what we need is to use the change of base formula in order to evaluate these things. Okay. So again, just as before, we still have all of these properties hold. The product, quotient, and power rules still hold for natural logarithms, but we just restate them here just to remind you. And again, these inverse properties here, this property 7 and 8, these also still hold. All right, but again, now just note that your base is now E in each of these examples. Okay, so now in this equation, we want to solve for y. So what we need to do, and again, anytime you want to solve one of these logarithmic equations, first thing you need to do is combine your logarithms on each side, right? So we want to say at the left side, this is the quotient rule. So this says natural log of y over x minus 7 is now equal to t. And now we're just going to use the exponential form of this. So this is now saying e to the t, right, is equal to y over x minus 7. So if I want to solve this for y, the last thing that we need to do is just multiply both sides by the denominator. So we're going to get that x minus 7 times e to the t is equal to y. And now we've solved the equation for y. So now note that in this case, because we have more than one variable, we're not going to get an actual number, but that's fine. So we just get this relationship between y, x, and t, which is perfectly fine. Okay, now in this next example, we should be able to explicitly get a value for t. Okay, so what do we need to do? Well, we see that we have our variable in the exponent, so we want to try and convert this to logarithmic form. Right, now when we do that, I would first need to divide both sides by 45. So that way the left side, if we reduce 15 over 45, we're going to get a 1 over 3. And then we're left with e to the negative 0.7t. Now, if we convert to logarithmic form, well, what does this look like? Well, a log with base e is a natural log, right? So this is going to be natural log of 1/3 is equal to negative 0.7t. So now all we need to do to get t is just divide both sides by the negative 0.7. So we'll get that t is whatever natural log of 1/3 over over just negative 0.7. And of course, we'll let the calculator do this. So I need an ln of 1 divided by 3. And then once I close that parenthesis, I need to divide the whole thing by negative 0.7. And we're going to get that t is roughly 1.5694. All right, so that's my t value here. Okay, so hopefully that's not too difficult. Now, in example 7, we're going to sort of do the same problem that we just did, only now we're replacing each of these values with sort of an arbitrary variable here. right? Well, what do we need to do? First, we need to get our exponential by itself. So the first thing we need to do is divide by b on both sides. So if we do that, we have a over b is equal to e to the k times t, right? And now we'll convert to logarithmic form. And if we do that, we're going to get a natural log, right? Because that's a log with base e. So natural log of a over b is equal to k times t. So if I want to get t by itself, the last thing I need to do is divide both sides by k. So we get that t is equal to natural log of a over b, all divided by k. And again, we don't have specific values for a, b, or k, so this is the best we can do in this case. All right. Now, this is essentially showing us, this is sort of pushing us in the right direction for what we're going to look at next, which is solving some exponential growth and decay problems. So this is sort of like a nice, interesting application of natural exponential problems. Okay, so if you have a quantity either increasing or decreasing at an exponential rate, we can have basically model the behavior by this formula here, right? So we have P is equal to P sub 0 times e to the kt, right? So of course, in this case, you have that P0 is some sort of starting amount. And then K is like a growth or decay rate. So this is usually a percent. And of course, T is the time. So whether it's minutes, hours, or years, or something like that. And then P is the ending amount. All right. So we're actually going to take a look at a couple of those problems. Okay. So in number 8 here, we want to suppose that $100 is invested at 4% compounded continuously. So we talked about compound interest before. The idea of compounding continuously just means that you are compounding it sort of at every instant, right? So it's an infinite number of times per year, right? So that changes our formula that we previously had. So we're going to use the exponential growth and decay formula, right? So we want to use P is equal to P0 times e to the k times t, right? Well, what's our starting amount? Our starting amount is $100. Right? Our growth rate, our K, is 4%. So as a decimal, that's 0.04. And T, we're given is 5 years. So using all this information, we now can say that our ending amount P is equal to 100 times e to the K, which is 0.04, times T, which is 5. Right? So now if we enter this in the calculator, again, you want to be careful. If you're entering this all in one shot, this exponent needs to be in its own set of parentheses. But anyway, we'll do 100 times e to the 0.04. And we want to multiply that by 5. Make sure my entire exponent is in parentheses. And we'll get that P is equal to $122.14. And again, we're talking money, so we will round it to 2 decimal places. All right, so hopefully that's not too bad. In part B, we want to know how long will it take for the account to double in value. So now we have a slightly different problem, right? Because now we know that our initial amount is 100. My growth rate is still 0.04, but we don't know T. That's what we need to solve for. Now, of course, if we're doubling, they don't tell us exactly what P is, but we can get it, right? Because we just take P0 as 100. If we start with 100, we want to end with 200. All right, and then that would be doubling. Now, it turns out that in each of these, so if you have like a doubling problem, you actually don't even need the initial amount, right? So you could always just say, if you weren't given the initial amount, make this 1. Make it easy for yourself. Make this 1 if not given. So then if you want it to double, you would just want P to be 2. And of course, that's if it's not given. All right, but in this case, we are given it, so we can just use the information that we have. So anyway, if we plug all this in, we have P, which is 200, is equal to P0, which is 100, and then times E to the K, 0.04 times T. So to solve this, I need to divide both sides by 100. And this is just like the problem that we did earlier. So if we reduce 200 over 100, we get 2. 100s cancel here, and I get E to the 0.04 times T. So finally, I can convert this to logarithmic form, and I will get that the natural log of 2, I won't do this yet, is equal to 0.04 T. So now to get T, we just need to divide by 0.04. So we get that T is equal to ln of 2 over 0.04. And if I find that my calculator, ln of 2 divided by 0.04, that gives me that T is roughly 17.3, let's see, 3287. All right, so it'll take a little bit over 17 years for this account to double in value. Okay, so in the next example, we're told that a radioactive isotope decays at negative 3.7% per year, right? So if 500 grams are present initially, how many grams remain after 10 years? So again, we need to use our exponential growth and decay formula. So we're starting with 500 grams, so that's P0. Now in this case, since we're decaying and we're not increasing, I need to make my K negative, right? So if we're decreasing by 3.7%, that's negative 0.037. And of course, my T is given to me, that's going to be 10. So if we put all this together, we get that P is equal to P0, which is 500, times E to the negative 0.037 times T. Or sorry, T is 10. They gave that to us. So I just need to multiply that by 10. Right, so if we do this in the calculator, we're going to get 500 times E to the negative 0.037. And then I need to multiply that by 10. And that will give me that P after 10 years is 345.3672. And of course, this is in grams. All right, so that's just another application of our growth and decay formula. Okay. So I think this is the last example. Yep, so this is the last example, and then we'll wrap this video up. So in this particular problem, we're given that the formula for estimating the amount of money, which is represented by capital A, spent on advertising a certain toy is A, is equal to 350 plus 650 ln of n, where n is the expected number of toys sold. So now we're told that if the company wishes to sell 100 toys, how much should they spend on advertising? Well, if they give us, I think that's 1,600, right? Yeah. So then we have 1,600 toys. If they're giving us the number of toys, that's an n value. So they're giving us that n is equal to 1,600. So now we just go to our formula, which is A is equal to 350 plus 650 ln of n, and we just plug in 1600. So plus 650 ln of 1600. So now if we let the calculator do it, we'll have 350 plus 650 ln of 1600. So if we do that, we get that A is roughly equal to $5,145.54. We'll round to 2 decimal places here since we're talking money. All right, so if they want to sell 1,600 toys, they should expect to spend about $5,145.54 on advertising, at least based on this model. Okay, now in part B, we want to know how many toys can be expected to be sold if $10,000 is spent on advertising. So now we're actually being given our A value. So this is telling us that A is 10,000. So again, our formula is A is equal to 350 plus 650 ln of n. So here, we just need to plug in this 10,000 for A and solve. So now we have 10,000, is equal to 350 plus 650 ln of n. So we can subtract 350 from both sides. And that will give us that we have a 9,650 is equal to 650 ln of n. So next we can divide both sides by 650. And let's see, does that work out nicely? So if we do 9650 divided by 650, all right, we do get a ugly decimal, so I'm going to leave it for now as 965 over 65. All right, and I guess we could reduce that further by dividing each of those by 5. And if we do that, we'll get a 193 over, I believe, let's see, 65 divided by 5 should be 13. Right, and that's equal to ln of n. So now since our variable is inside the natural log, we're going to convert this to exponential form. And natural log is base e, so we want e to the 193 over 13, and that would give me n. So if we plug this into the calculator, we're going to get e to the 193 over 13 should give us about, so we'll get n is 28,028,68.31. So it looks like we get 2,802,868.31. So I guess if we were selling toys, we would just round this up to the nearest whole number. This would be 2,802,869. All right, so that's probably the better answer. Okay, so that wraps up this video on natural logs and natural exponentials. I hope you enjoyed the video, and I will see you next time.